So here is another question on energy of simple harmonic motion. So it is given that a body weighing 10 to the power minus 2 kg has a velocity of 0.04 meter per second after 1 second of its start from the mean position. If the time period of this SHM motion is 8 seconds, we have to find its kinetic energy, potential energy and total energy. Okay, so first it is given, first let us write the basic SHM equation format. Okay, x is equal to a sine omega t. Here it is given that the time period t is equal to 8 seconds. Okay, so angular frequency we can determine omega, which is equal to 2 pi f is frequency in hertz, or 2 pi by capital T, because time period is the reciprocal of frequency. So it is equal to 2 pi by 8 seconds, so it is pi by 4 radians per second. Okay, omega is equal to pi by 4 radian per second. Here it is given after 1 second of its start, that is at t equals to 1 second, the velocity is equal to 0.04 meters per second. Now we know velocity is equal to dx by dt. This is the displacement equation. V is equal to dx by dt, which is equal to a omega cos omega t. So at t equals to 1 second, velocity is 0.04 meter per second. That implies 0.04 is equal to a omega, will substitute with pi by 4 angular frequency, cos omega again pi by 4, and t will replace with 1. That is at t equals to 1 second, velocity is 0.04. Our objective here is to determine the amplitude. So that implies a is equal to 0.04 into 4 by pi into cos pi by 4. So that is equal to how much? 0.072 it is coming, that is. So the amplitude of this SHM motion is 0.072 meters. Then we have to find the various energies. Okay, first for calculating the different energies, we'll need another thing, which is the force constant K. Force constant K is equal to m omega square, because we know angular frequency is root over of k by m, so k is equal to m omega square. So that is equal to 10 to the power minus 2 kg into omega square, which is equal to pi by 4 radians per second, that square. So it is coming around 6.16 into 10 to the power minus 3 Newton per meter. That is the force constant. Okay, that is the force constant K. Now we have to determine the various parameters. First, let us determine the total energy. Okay, total energy is equal to 1/2 K A square, equal to 1/2 into 6.16 into 10 to the power minus 3 into A, which is equal to 0.072 whole square. It is coming around 16 into 10 to the power minus 6 joules. That is the total energy. Okay, it is the total energy. Then let us calculate at t equals to 1 seconds. We have to determine the kinetic energy. We can determine that from the equation 1 half m v square, the velocity at t equals to 1 second, which we calculated. 1 half into mass, it is 10 to the power minus 2, into the velocity, which is given 0.04 meter per second, into 0.04 whole square. Okay, kinetic energy at t equals to 1 second. It is given the velocity at t equals to 1 second is this much, so simply we are substituting that value, and it is coming half, it is coming 8 into 10 to the power minus 6 joule. This is the kinetic energy. Now we know that throughout the SHM motion, sum of kinetic energy and potential energy is constant. That is, the total energy is always constant, no matter the position of the particle throughout the SHM motion at any given time, at any position, the sum of kinetic and potential energy will be constant. That is, total energy is constant. So here we can determine the potential energy EP is equal to ET minus EK. Okay, this is the potential energy at t equals to 1 second, and we are subtracting the kinetic energy at t equals to 1 second. So that is equal to 16 into 10 to the power minus 6 minus 8 into 10 to the power minus 6, which is equal to 8 into 10 to the power minus 6 joules. So here both the potential energy and kinetic energy, they are the same. Okay, so this is the thing. So we have determined total energy, kinetic energy, and here the potential energy. Okay.